So in this video, I'm going to talk about the question in thermal and statistical physics which appeared in GATE 2005 examination. So let's continue our discussion with the problem 1. The statement is, the equation of state for the gas with internal energy U is PV, that is equal to 1 by 3 U. Okay. Then the equation for an adiabatic process is, so we have to find the corresponding equation that will describe the adiabatic process for this equation of state. Okay. So because this is given to be adiabatic process, so that means we can write dq equal to 0. So let me first rewrite the equation of state, but pressure, that is 1/3 of energy density. Okay. So that let me call this as 1b and this is 1a. Okay. So because we are going to look for the equation for the adiabatic process, so that means for adiabatic process dq is equal to 0. Okay. So du from the first law, du, that is equal to dq minus dw. So dq, this is 0. Okay. So that is equal to minus p db. Okay. So let me call this as equation 2. Okay. So that means 2 can be written as p dv, that is equal to minus d of u, or that is equal to u is equal to 3 pb. Okay. So from equation 1a, so that means this is equal to minus d of 3 pb. Okay. So this can be further rewritten as minus 3, its constant, minus 3 p dv minus 3 b dp. Okay. And after rearranging these terms, so bring p dv on the left hand side, so it becomes 4 p dv is equal to minus 3v dp. Okay. Or this can be rewritten as 3 p dv plus 3v dp, and that is equal to 0. So let's call this as equation 3. Okay. So divide this equation by pb. So divide 3 by pb to get 4 db by v. So we obtain 4 dv by b plus 3 dp by p, and that is equal to 0. Okay. So now call this as equation 4 and do the integration. Okay. So then we obtain 4 ln b. So from equation 4 ln b plus 3 ln p equal to constant. Okay. So I can write ln b power 4 plus ln p power 3 equal to constant. Okay. Or this can be written as ln b power 4 p power 3 equal to constant. So this implies p power 3 b power 4 is constant, or I can write p b power 4 by 3, that is equal to constant. Okay. So that means the correct option is C here. Okay. So that's the required equation describing the adiabatic process. Okay. And let's take a look at the next problem. The statement is, the total number of accessible states of n non-interacting particles of spin half. Okay. So here, because it's not mentioned, because it's given that particles carry a spin equal to 1 by 2. So that means these are fermions, because half integrals mean spin, so imply fermion. Okay, so that means they are want to satisfy the Pauli exclusion principle. Which implies that we cannot accommodate more than one particle in a single particle state. Okay, not more than one particle is allowed in single particle state. Okay, so that means we will have as much number of states as much number of particles, so they will be equivalent. So therefore here number of states will be equal to number of particle. Okay, because here we are, there is no hint which is available, so that particle can have a the spin of -half. So therefore based upon the information that is shared in the question, so we will have the number of particles exactly equal to the number of states, because we can only put one single particle in a one particular energy state. So that will give rise to n number of states. So therefore here option D is the correct one. Let's continue with the next problem. The pressure for a non-interacting Fermi gas with internal energy U at temperature T is. Okay, so here when we talk about a 3D Fermi system, so for 3D Fermi system, for 3D Fermi gas, so we are having the total energy for such a system is given as n, the total number of fermion in the system, multiplied by the average energy per fermion. Okay, and that is equal to 3 by 5 times n multiplied by the Fermi energy. So here we have made use of the fact that the average energy per fermion is equal to 3 by 5 of the Fermi energy. So okay, so that means let me call this as equation 1, and here Fermi energy EF, that is equal to h cut square upon 2m multiplied by 3 pi square n by b power 2 by 3. Okay, so now the total energy for this system is equal to E, that is equal to 3 by 5 NEF. So that means 3 by 5 n multiplied by EF, that is equal to h cut square upon 2m and 3 pi square n by b power 2 by 3. Okay, and what I can do is I can write this as C divided by b power 2 by 3. So this I have done intentionally because I am going to evaluate the pressure which can be obtained by differentiating E with respect to b by keeping all rest of the terms as constants. So that's why I have clubbed all the constant terms here in this expression in constant C here. Okay, so now pressure is equal to, so because we know that du, that is equal to TdS minus PdV. So from here, because here instead of U we are taking sign E here, so I P from here, that is equal to minus du by dV by keeping S constant, or that is equal to minus dE by dV by keeping S constant. The U and E, they carry the same meaning. Okay, so P is equal to minus dE by dV by keeping all other terms constant. So that is equal to, so differentiate this equation with respect to B. So we obtain minus C dd B of 1 upon B power 2 by 3. So after differentiation, what we obtain is minus C and then the exponent minus 2 by 3 and V power minus 2 by 3 minus 1, and that's nothing but that is equal to 2 by 3, minus minus will become plus, and then we will have C divided by B power 2 by 3. So that is nothing but that's E. C divided by B power 2 by 3, that's E, and then we have additional B power minus 1, so that will give you V. Okay, so that means pressure is equal to 2/3 of energy density. So that's our final result here. Okay, so therefore option B is the correct one here. Let's take a look at the next problem. So it is a system of non-interacting Fermi particle with Fermi energy EF has the density of states which are proportional to under root E, where E is the energy of the particle. The average energy per particle at absolute zero is how much? Okay, so here we will apply the definition of the average energy. So average energy, that is equal to 0 to EF, okay, and then E, because we are talking about the average of energy, so that's why energy will come into picture here. F of E, that's a probability distribution function, and multiplied by the density of state GE dE, okay, and then divided by 0 to EF, and then again F of E, that's a probability distribution function, multiplied by density of state GE dE. Notice that the we have already in one of my previous video from GATE examination, I have already talked about the properties of the Fermi direct probability distribution function F of E, that is equal to 1 over 1 plus exponential E minus EF upon KT. So this function has a behavior of this type, okay, at absolute zero. Okay, so we are talking about the properties of the Fermi system at absolute zero. So this is F of E as a function of E. Okay, so this represents the Fermi energy basically. So for an energy smaller than EF, all the states below the Fermi energy, they are occupied, and this probability distribution function has a value of unity, and the value of this probability distribution function become equal to 0 for all energy greater than EF values. Okay, so therefore we are doing the calculation only from 0 to EF, and we are neglecting the higher energy states, okay, because in that case Fe will be 0. So here up to EF it is equal to unity, this is also equal to unity, and this integral turns out to be equal to 0 to EF E as it is, and then density of states E power 1 by 2 dE. So in principle we will have some constant terms associated with GE dE, so they will appear as a pre-multiplier here in this integral here, and because they are also common in the denominator also, so ultimately these terms they will cancel with each other. So 0 to EF, Fe is equal to 1 here as I have written, so then GE dE E power 1 by 2 dE, okay. So that is equal to 2 by 5 into EF power 5 by 2, okay, divided by 2 by 3 EF power 3 by 2, okay, and that is equal to the average energy, that is equal to 3 by 5 EF. Okay, so that's the final answer here. So therefore right option is D here. So let's continue with the next problem. The statement is the partition function of two Bose particles, each of which can occupy any of the two energy levels 0 and E. So we are having n is equal to two particles which are bosons, and we have to accommodate them in two energy levels with energy 0 and E. Okay, so the possible configurations are either both of them could be in the ground state, the second possibility is both of them could be in the energy state E, or the other possibility is that one of them is in the ground state and another one in the excited state. Okay, so now the for this configuration the energy is 0, and here it's 2E, and here it is E. So the corresponding partition function is Z, that is summation exponential minus beta I taking value from 1 to 3. Okay, so that is equal to, so for the first energy term it's 1 exponential minus beta E0, that's 1, plus exponential minus 2 beta E plus exponential minus beta E. Okay, so therefore option 2 is correct here. So let's continue with the next problem. So it is if the partition function of a harmonic oscillator with frequency omega at a temperature T is, okay, so we are given the partition function of the harmonic oscillator, which is Z1, that is equal to kT upon h cut omega. That's the partition function. Okay, so this implies partition function for n such objects or particles, that is equal to Z1 power n. Okay, so that is equal to kVt upon h cut omega power n. So the free energy for n such independent harmonic oscillator, the free energy for n such independent harmonic oscillator is given by A is equal to minus kVt ln Zn. So that is equal to minus n kVt ln kVt upon h cut omega. So that is equal to n kVt ln h cut omega by kVt. That is our final answer. So this is n kT ln h cut omega by kT. So therefore C is correct option. So let's take a look at the next problem. The statement is the number of states for a system of n identical free particles. So we are having n identical and free particles in three-dimensional space having total energy between E to E plus delta E, where delta is much smaller than E is proportional to. Okay, so for the single free particle, for a single free particle in free space, degree of freedom they are equal to 3. Okay, so for n free particles in space, the degree of freedom equal to 3n, and we call this as d. Okay, also for a free particle E is equal to p square by 2m. So this implies s is equal to 2. Okay, so here s is the exponent of p basically. Okay, so exponent is 2 here. Okay, so density of state with energy, density of state with energy less than equal to E is proportional to E power d by s. Okay, where d refers to the degree of freedom basically. Okay, so it is written as, that is omega E, which denotes the number of states with energy less than equal to E, that is proportional to E power d by s. Now the density of states in the energy then E to E plus delta E, that's given by that, or denoted by omega dash E, that is equal to d omega E upon dE multiplied by dE, that is proportional to E power d by s minus 1. So here in present case here d is equal to 3n and s, that's the exponent of p, which is 2, s is equal to 2. So therefore required density of states is proportional to e power dys minus 1, so e power 3ny2 minus 1, okay, and then dE. So it represents the density of states in the range e to e plus delta e, okay. So therefore right answer is A. So let's continue with next problem. The statement is energy of a ferromagnet as a function of magnetization is given by this expression, okay. So the number of minima in the function fm for t greater than tc, okay. So here I'm going to discuss the qualitative variation of the this free energy as a function of order parameter, which is the magnetization basically, for 3 different situations when there is no applied external field. So that means the essential condition that I'm considering here, then when there is no external field, that is h is equal to 0, okay. It's a no field condition. So in this case we will have 3 situations depending upon whether we are working below the critical temperature, or we are working at critical temperature, or we are above critical temperature, okay. So here let me draw these diagrams qualitatively. So for t greater than tc we are having variation in the Helmholtz free energy. It's a parabolic basically, like this, and this is for t greater than tc, okay. And on the y-axis it is free energy F as a function of order parameter eta, which is magnetization, okay. So this is a situation for t greater than tc, okay. And similarly one can conclude the discussion for the case when t is equal to tc. So at t is equal to tc, so a flat portion appear in the minima, okay. So these are the qualitative differences that one must keep in mind while talking about the free energy in a magnetic system. And in the third case, when we are talking about the temperature smaller than critical temperature, so something like this, okay. So this is a situation when t is smaller than tc and it is the free energy, and here we are having order parameter, okay. So here these minima, they are placed symmetrically with respect to this eta is equal to 0 value. So therefore we notice that for temperature greater than tc, the number of minima in the function fm, there is only one, okay. So therefore b is the correct option. So this corresponds to this situation. A one-dimensional random walker takes steps to left or right with equal probability. So that means here we are given that p is equal to q, that is equal to 1 by 2. The probability that random walker after starting from the origin is back to origin after n even number of step is, okay. So we are given n, which is an even number, okay. So suppose a person starts from a certain region, and if he or she is taking some steps towards the right, and then he will be exactly at the same position when the number of steps taken to the right there, that exactly matches with the number of steps taken to the left. So that means when number of steps is towards either direction, that is equal to n by 2. So it's only possible in this situation. So therefore the corresponding probability, which is equal to w n1, that is equal to n by 2, and that is equal to the n factorial, that is the factorial of total number of steps, divided by n1 factorial, which is n by 2 factorial, and then n2 factorial, which is again n by 2 factorial, and then p power n1, p is 1 by 2 and its power n1, which is n by 2, and then q power, which is 1 by 2 again, n by 2, okay. And this is nothing but n factorial divided by n by 2 factorial into n by 2 factorial, and then 1 by 2 power n. So therefore option A is the correct one here. Let's continue with last problem. Density of states of free electron in solid moving with an energy 0.1 electron volt is given by this expression. So we are having a situation here when energy of the electron, it is 0.1 electron volt, corresponding density of state that is equal to 2.15 into 10 power 21 per electron volt per centimeter cube. Okay, now when the energy of the electron is changed to E2, that is equal to 0.4 electron volt, the corresponding density of states will be how much? Okay, so for the three-dimensional system, the density of states, we know that it is proportional to e power 1 by 2. So in the second case, the energy has increased by a factor of 2. Okay, so that means in the second case, density of states for the second case, they will be connected with the density of states the first case, that's increased by a factor of 4 power 1 by 2. So that's equal to 4 power 1 by 2 and e power initial density of state, density of state 1. Okay, it's merely a factor of a difference of this factor. So it is basically 2 times density of state with the initial state, that which I am calling as 1. So that means in the second case, the density of states will be 2 times multiplied by 2.15 into 10 power 21. So that is equal to 4.3 into 10 power 21. So therefore D is the correct option here.